questions? So you're understanding all the material?
More or less.
What's the less part?
Like the new stuff that we did yesterday, the polarity, the little pieces.
Any questions about that?
Right after today, I'll.
Okay. Understand hybridization?
Yeah, I understand.
No questions about hybridization? Yes.
All right, so just to confirm what we were talking about with the nitrogen with the special case, if it has the lone pair and it's near a pi bond, it acts like it's in the p orbital, and that's when it goes to sp2.
If the lone pair is next to a p orbital, it's going to want to be in the p orbital, unless there's some reason it can't.
Not just
Usually it looks like it's sp3, but because of this exception, it'll be sp2. The lone pair will be in a p orbital. It'll be trigonal planar. Lone pair in the p orbital, because it's interacting with the next door p orbital. This is conjugation, also known as resonance. Resonance of a lone pair. Yes. Understanding what type of electrons thus a compound has, pi electrons versus sigma electrons. Today we might look at yellow Kevlar, make a bulletproof vest out of. Yep. All right, let's get started. Let's look at, we left off with polarity. We'll probably have a quiz on Monday. Okay, where did we leave off at? We did SO2. What about carbon tetrachloride? Carbon tetrachloride. Carbon with 4 chlorines. Let's see. Chlorine. This carbon is going to be tetrahedral. It's going to be 2 in the plane, 1 forward, and 1 back. We have dipoles to every chlorine. Those are equal. Are they going to cancel each other out? Carbon with 4 chlorines around it in a tetrahedral manner, yes, they will cancel each other out, because one pulling up is canceled by 3 coming like this, because these 3 sort of sum up to have one this way, or this one has one this way, and they will cancel out. Carbon tetrachloride is nonpolar, a nonpolar molecule, because the vectors cancel each other out. Any tetrahedral with 4 identical things is always going to be nonpolar. What about chloroform, where instead of having 4 chlorines, it's only 1? Put the H here. So now there's no dipole. And so if this is just an H, there's no dipole pulling up. Maybe if you want to change that to something else. Only thing you have is the 3 chlorines pulling boom, boom, boom. And if you sum those up, they're pulling straight down. So this is going to be the negative end of the molecule, and this will be the positive end of the molecule, because the electrons are just being pulled this way. And the sigma bond, the electrons in the sigma bond here are going to be sort of polarized a little bit as a result of the chlorine pulling, like tug of war. These pull. They make the carbon partial positive, but they also a little bit make the H partial positive. It's pulling this way. If we show a molecular dipole moment, I reckon sort of hard to see the 3D nature, but we got it straight down, sort of the direction of the dipole moment. hard to see here, but if you saw it here, okay, that chlorine's supposed to be going back. This chlorine's supposed to be coming forward, but the dipole arrow goes straight down the gut. Yeah. Okay. You have to visualize it here, which is the summation of the three individual dipole vectors. Okay, which is next? So chloroform is polar, yeah? So the molecular dipole moment. What about CH2, Cl2? Dichloromethane. You could call this trichloromethane, but it goes by the name of chloroform. Okay? This is dichloromethane. Basically, now you have two H's. We were racing good earlier. Two H's.
There's another one over there.
Do it.
There's another one over there. Oh.
All right. That's
What if we had two chlorines? Make the H's yellow, two chlorines. Are they equal and opposite? Of course they're equal, they're both CCl bonds. Are they equal and opposite? No, they're both coming like this. If this one was coming this way, the other one had to be coming this way to cancel. They're not, they're tetrahedral. It's not linear, okay? If they were linear, they would cancel. Because of the tetrahedral nature, they're not. And so this is also polar. Ionics. Well, ionics are just the extreme. Of course, if you wanted to show this covalently for some reason, you would say, hey, chlorine is way much more electronegative. And so it's going to be pulling, leaving partial minus, partial plus, yeah? Or you can show a dipole arrow. Of course, typically you're taught that group 1, group 2 does not make covalent bonds. Why? Because the chlorine is, even if it was originally like this, it's so much more electronegative than the sodium. It pulls the electrons, it just takes them away. Okay? Extreme pulling. Takes them away, and you can just say, hey, I'm going to move these electrons onto chlorine, give the chlorine the fourth lone pair, it's minus, the sodium is now plus, and it's now ionic. But that's actually how it exists, because of the extreme difference in electronegativity. Of course, this exists in sort of a unit cell, because all these ions do attract to each other. That's the extreme. But in the end, it's a good rule, group 1, group 2, never make covalent bonds with those. Okay? And I see it all the time. You guys all the time want to draw a dash between like a sodium and a chlorine, or a sodium and some other ion. Don't do that. Okay? That's okay to just say sodium chloride. There's no dash there. That's essentially just formula. As soon as you do that, you're wrong. Right? Okay, those are some simplistic polarities. In most larger molecules, it's kind of rare that the dipoles will cancel. You have to really see some symmetry there and assess it. Simple molecules, you can easily have cancellation non-polar, like CO2 and carbon tetrachloride. Okay, let's look at physical properties. We're going to look at two main things, boiling point, melting point, and then solubility. First, boiling point, melting point. Okay, to get a compound to boil, we got to vaporize it, yeah? To vaporize it, you got to get the individual molecules to no longer be attracted to each other. So you have to break the intermolecular attraction. The IMFs, intermolecular forces, you got to break those forces to get the molecules to separate and move into the gaseous phase. Okay? It's like you guys, if you're different molecules, okay, 60 molecules. In the liquid state, you're sort of kind of holding hands. All right, that would be an IMF. In the solid state, you're kind of holding it all together, arms and everything. You know, but still holding hands. We got to put in energy to get you guys to break the hand holding or some other IMF. But in general, the higher intermolecular attraction or the higher IMFs, okay, the higher degree of IMFs, the higher the boiling point. Types of IMFs. They're here. There's 4. They're in order of strength. Van der Waals attraction is going to be the weakest. The strongest is going to be ionic attractions. We'll go through each of these one at a time. Okay. First, Van der Waals attraction, sometimes also called London forces or dispersion forces. To me, it's the same thing, but there's some fine differences. Look at these 3 different hydrocarbons. Just hydrogen and carbon. That's why we call them hydrocarbons. Saturated hydrocarbons. Boiling point. This guy here, 1, 2, 3. What do you want to call that compound? Propane. 3 carbon, ane. Okay, propane. Boiling point at negative 4.2. That means it is a gas at room temperature. Okay, 1, 2, 3, 4, 5. Pentane. Boiling point higher. 36. It's a liquid at room temperature. And then we go to this branched 1, 2, 3, 4, 5. You can probably name it. What is that? 2,2-dimethyl propane? Yeah. 3 carbons, 5 carbons. Still 5. But this 5 is much lower than that one. Why the trend? This is basically because of Van der Waals attractions. And we have more Van der Waals attractions here. Van der Waals attractions are pretty weak, fleeting. It's attraction due to weak temporary dipoles induced, induction, you may hear in physics, induced by molecular contact. Yes, this compound is nonpolar. It's just CHs. We call it nonpolar. But if you had a sample of that compound, those electrons can be influenced by surroundings, and even at the very molecular level, there can be some sort of instantaneous or fleeting polarization of the electrons. Okay. Again, this can be influenced by the surroundings of the molecule. But this is going on. And as soon as one molecule is influenced and it becomes polarized for some reason, okay, then it can induce the next door molecule to become polarized. And so you get this induction. Very weak. You'll talk about electrical polarization in physics. Now, one thing can polarize another thing, but really it's the molecules in those things that are polarizing each other. In the end, the take-home here is the more surface area a compound has, the more it's going to polarize its neighbor as it comes into contact with it. The surface area here, kind of circle it, you see the larger compound has more surface area. And if this molecule is polarized somehow, even just instantaneous at the molecular level, or it became polarized by something in the surroundings, maybe there's an electric field nearby that polarizes it, then boom, then it polarizes the next guy. And as it polarizes the next guy, you get some partial minus and partial plus created, and they just start sort of coming together. Very weak. Okay? Take home though, the more surface area, the more this can happen, and this is thus a greater IMF. Greater attraction between the molecules. Greater attraction between the molecules, thus the boiling point is higher. We get to this guy over here, why does it go low again, even though it's 5 carbons? Because it's branched. And if you look at this, and you look at this, that carbon in the center is sort of hidden. Okay? and it doesn't contribute as much to the surface area. In the end, the take-home is branching lowers your surface area, but branching also thus lowers your boiling point. Why? Because branching lowers the IMFs. You can keep going. Less IMFs means the molecules aren't holding hands as tight by this very weak van der Waals attraction that we tried to describe. So now we can explain the trend. This is higher than that one, more surface area. These two, they're constitutional isomers. Same formula, different connectivity. We would predict lower boiling point for this guy because it has less surface area. Okay, that's van der Waals. Induction, very weak. There's no permanent dipole there. It's an induced dipole. Let's leave number 2, which is dipole-dipole. Here we're going to have permanent dipoles. Consider these 3. 1, 2, 3, 4. Pentane, 36, same as up there. We put a carbonyl here and get this ketone, very similar size. The boiling point goes way up, 76. It's also up for this guy. But these two both have permanent dipoles. Permanent dipoles are stronger than that very weak induced dipole stuff. And so that right there explains what? And when you got dipoles, what's going on? Of course, here's the dipole for the carbonyl. The partial minus is going to be very attractive to the partial plus of another molecule. So these are holding hands pretty strong. Where this up here, they were just sort of pinky. Okay? That's weak. All right? It's fleeting stuff. Got a permanent dipole. Now we're like, hey, we're more attracted. Permanent dipoles. Both of these do, you see, similar. Now you can't start mixing apples and oranges. I could show you an alkane that had about 40 carbons, and it would have a higher boiling point than this. Because the surface area can be so huge that it can amount to something. Typically, we want to compare similar sized compounds. So this is sort of the dipole-dipole interaction that we're showing. And we're showing the interaction with sort of a dashed bond. To show that non-covalent interaction. Non-covalent interaction. It's not a true bond. All of that non-covalent interaction. Dipole-dipole interaction. Okay, what's number 3? 3 is hydrogen bonding. Hydrogen bonding is just a special type of dipole-dipole interaction. It gets its own name because it's very strong. Compare these two compounds. Here we do have a dipole, 78. This guy is higher, and we would predict higher, 118. Why? Well, hydrogen bonding. What is hydrogen bonding? It's a particularly strong interaction that occurs between oxygen, nitrogen, or fluorine lone pair. That's those guys right here. And a hydrogen that is bonded to an oxygen, nitrogen, or fluorine. So that's these guys right here. Okay, it's between a lone pair and an H, but the lone pair has to be on an O, N, or F. And so these lone pairs, which are electrons, and electrons have a negative charge, will be attracted to the H, and H, which is on an O, N, or F. Now, these have a dipole. All these bonds do, right? And it's a pretty strong dipole because these are 3 very electronegative atoms, leaving the H here partial plus. Okay, good. Thus, these electrons will be attracted to the partial plus. Electrons are minors. Any of these, I mean, you can hydrogen bond. The lone pair is called the acceptor, the hydrogen bond acceptor. The H that's on an O and an F is called the hydrogen bond donor. It's just a special type of dipole-dipole. But it's particularly strong because the H can become very electropositive, being bonded over there, very polarized. And these atoms, the lone pairs, are very electron-rich. Of course, we can show the hydrogen bonding just like we showed with the dipole-dipole, something like this. And so for the alcohol up here, I'm showing the lone pair sort of doing a non-covalent interaction with the H. You can have a hydrogen bonding network here. This O can hydrogen bond to the H, while another O can hydrogen bond to the H that's bonded to that O. Basically, all these molecules can now be holding hands, particularly tight, very tight. And it's a strong dipole-dipole. This guy over here cannot do hydrogen bonding. We got to recognize, hey, these molecules can hydrogen bond to themselves. This molecule cannot. It can only have dipole-dipole. So we predict a higher boiling point for the other. What about this ether? Can it hydrogen bond to itself? Can it hydrogen bond to itself? If every one of you was one of these molecules, could you hydrogen bond to your neighbor? Does it have a hydrogen bond acceptor?
It has the acceptor on it.
Why do you say no, Glenn? What are the acceptors? Oxygen lone pair, nitrogen lone pair, or an F lone pair? Does it have an oxygen lone pair?
Yes, but it doesn't go to go with the acceptor.
Correct. But it does have a acceptor. Does it have an H bond donor? Does it have an H bonded to a O and an F? No. It only has an acceptor. There's no donor. It's like Velcro. Don't you have to have two different pieces of Velcro? You have to have this kind of the fuzzy piece and then the more woven piece. If you had two of the same pieces, would they stick together and do the Velcro thing? No, you have to, okay, you have to have two different pieces. Okay. Can it hydrogen bond to itself? No. But you got to be careful when you ask this type of question. Can this hydrogen bond to water? Yes, it can. Okay. If we had water, this would act as an acceptor, and the water hydrogen could act as a donor, and it could hydrogen bond to water. Or any other hydrogen bond donor. How many H bond acceptors and donors are present in the antidepressant effexor? This can be a little, the acceptors can be a little vague. We may have to clarify that question. First off, how many hydrogen bond donors?
One.
One? One, right there. Now, since a hydrogen on an O and or F is always drawn in, pretty simplistic, the hydrogen bond donor is going to be drawn in. Is a CH a hydrogen bond donor? No. No, it's OH, NH, or FH. 1. How many acceptors?
3.
How many?
3.
Anybody else?
3.
Anybody else? Okay, here's where the vagary comes from the question. There's 5 lone pairs. Is each one a acceptor? Or is it just, or is just the oxygen just come one? I mean, can each lone pair do a hydrogen bond? What if it's in methanol or something? Maybe that one can, and then maybe that one can. Can each lone pair hydrogen bond? I think that's a vagary in the question. I think sometimes it can, they can, sometimes not. I would modify this question and say acceptor atoms. How many acceptor atoms? 3. Otherwise, you have to kind of clarify. You say, hey, are you talking about, should I count the lone pairs as 2 or just the all polar oxygen as 1? See what I'm saying? So I would probably want to say atoms. Let's look at some examples of this. Look at this alcohol versus this ether, the constitutional isomer, same formula. One of them has a lot higher boiling point. Why?
Hydrogen bonding.
Hydrogen bonding, very good. I'm joking. We're on topic 3, hydrogen bonding. Hydrogen bonding will be the answer to lots of questions. Make sure you don't just say hydrogen bonding. Sometimes I hear students say hydrogen bonding. No, not here. Okay, these amines, primary amine versus tertiary. Why has this one got a higher boiling point? Hydrogen bonding. This guy can hydrogen bond to itself. You should be able to show that. Understand why? Can that hydrogen bond to itself? No. It has an acceptor, but there ain't no donors there. The next door molecule has just got another acceptor. 2 acceptors ain't going to do anything. They'll actually kind of repel each other. Explain the trend. Water, 100 degrees. H2S, minus 60. 160 degrees difference. Why? Hydrogen bonding. Water has both an acceptor and a donor. So you're sitting next door to a water molecule. Let's say your acceptor is interacting with somebody else's donor. Or maybe your donor is interacting with somebody else's acceptor. Water actually has both, either way you want to do it. H2S has neither. Okay? There's no lone pair on an oxygen, nitrogen, or fluorine. There's no H on an oxygen, nitrogen, or fluorine. You may say, well, isn't sulfur just below oxygen? Yeah, you do have a dipole here. But it ain't a hydrogen bond. And hydrogen bond is a very strong, and it gets its own name. And you see the big difference. That's why it gets its own name, because it's such a big factor. This does have dipole-dipole. You go to methane, there's not even dipoles there. And it's minus 162. Boiling point gets real low. The only thing holding these molecules together is what? Van der Waals. And since it's just one carbon, there ain't much surface area. So there's hardly anything holding those molecules together. Below, antifreeze. Look at butane. It's gas at room temperature. Unless you put it under pressure like in a lighter, then you can liquefy it. But a very similar molecule, very similar molecular weight. You put 2 H's on the end, and so that the carbons, when you make this sort of dialcohol on a diol, the boiling point goes up 200 degrees. Those molecules are held together very strongly by what? Hydrogen bonding. Hydrogen bonding holds holds your DNA together. Four different types of bases. Your ATs hydrogen bond together, and then your CGs hydrogen bond together. These side chain residues of cytosine are set up very nicely to hydrogen bond with guanine. You have an NH hydrogen bonding to an oxygen acceptor. An NH donor hydrogen bonding to a nitrogen. Now they're lone pairs here, yeah? Lone pairs. Okay. You're showing the interaction there between the acceptor and the donor. You get these three because those molecules are very nicely set to do this. That's why C and G typically are linked together. The AT, there's only two hydrogen bonding holding them together. Because if you look at this other oxygen, this molecule doesn't have donor sitting close by that it can hydrogen bond to. Hydrogen bonding in many other applications. Kevlar, which is used to make like bulletproof vests, many other materials. Very strong. Gloves that cannot be cut. Surfboards that won't break, etc. Many applications. Kevlar is actually a polymer. And this just keeps going on and on and on, forever and ever. In red here is the monomer, where this is a repeating unit. You just keep repeating it, keep repeating it, keep repeating it. It's called a polyaramid. Ara coming from aromatic. We see these aromatic rings. And then amide or amide, because it has amide functional groups connecting all along, called an aramid. One long polymer chain, but these polymer chains, they line up. Why? Hydrogen bonding. And they're set up to nicely, this oxygen can hydrogen bond to that H, boom, boom, boom. And so the hydrogen bonding holds these polymer chains together, and you can just stack them on each other, and it builds up to then we can get to more of a macroscopic structure. That's just a repeat of what I told you over there. It's amazing how those molecules can be turned into fibers, and then those fibers can be turned into something useful, like clothing or any other thing. But hydrogen bonding, and hydrogen bonding is hard to break. Even a bullet can't break it most of the time. Amazing to go think about going from the molecular level to this more application fibers, but understanding that ultimately it's the molecular level that produces a lot of the properties. Next would be ionic attraction. Ionic attraction is the strongest. Okay. Because here we have actual formal charges, which are going to be stronger than a partial charge, or dipole. So your stronger is IMF. Boiling point of sodium chloride, about 14, 13. I've never seen anybody distill sodium chloride. Apparently somebody has, or I don't know if that's predicted or what. But very high. More reasonable example, ethanol, boiling point is 78. Okay? But if you take the sodium salt, the boiling point goes up to greater than 500 degrees. Because it's now ionic. Well, this is a liquid at room temperature. This is a solid at room temperature, because this is going to have a huge amount of IMFs, because those dipoles, not dipoles, those charged species just stick together very strongly. Very hard to separate them. Very high boiling point. And actually, the more IMFs you get, the more likely you are to be a solid. Okay, so those are your main IMFs in order of strength. Any questions about the IMFs? The warm-up page probably has some good questions, applications, some type of questions we've received. Questions, Glad?
In Chem 2, the valuable forces, we just call it the dispersion force.
Van der Waals?
Yeah.
Dispersion, to me that means the same. Again, I think there's fine differences, but London forces, I usually say Van der Waals. Okay, let's look at solubility. First, let's look at melting point. Melting point is very similar arguments throughout. To get a compound to melt from the solid phase to the liquid phase, you have to break some of the IMFs so the molecules can start becoming more mobile and become fluid. Okay? It's a very similar argument. You have to assess the IMFs that are there. If we do a relative comparison, for example, we can say, which one of these compounds has the higher melting point? One of them is 126, the other's 44. Which one would you expect to have the highest? Which one's 126? Gabriel? One on the left, why? Hydrogen bonding? Explain what do you see hydrogen bonding by? Could you show the hydrogen bonding network or something? One molecule, and we can maybe show another, NH2 of another. Okay, and we can maybe show these electrons, hydrogen bonding to that hydrogen bond donor. Okay? Of course, if you drew these H's out, then you can show another molecule. Okay? Show all these just sticking together by a hydrogen bond. Can this hydrogen bond to itself? No. I see hydrogen bond acceptors, but there's no donor. So if you drew a neighboring molecule, what hydrogen bond would you show? You wouldn't be able to show them. So you can't hydrogen bond to itself. So if you have a pure compound in a solid form, it's not hydrogen bonding. It's only the only IMFs it has is just dipole-dipole. It does have that, but not the magically strong hydrogen bonding. Solubility. Of course, we're doing that in lab this week. Main thing to remember is the old adage, like dissolves like. A compound will dissolve best in a solvent that has similar IMFs. And the more IMFs that you can envision, then typically that's going to help the solubility. For example, let's look up here. One other thing to say here is that if you have different IMFs, they're typically going to not like each other. For example, which of these amides up here would be most soluble in hexane? On the left or right?
The right.
One on the right, because hexane is nothing but a hydrocarbon. Okay? It all it has is van der Waals. This guy is held together by hydrogen bonding. Why would it want to break apart from each other and you can start associating with hexane? It wouldn't want to. It can't hydrogen bond to hexane. Okay. On the other hand, this guy is not held together as tightly. So it's going to be more reasonable to say that hexane is going to be able to get in here and sort of move it, get in between those molecules, break them up, and dissolve them, dissolve the compound. So in terms of like dissolves like, up here we say, hey, this compound's more polar. Hydrogen bonding is considered a polar thing. Less hydrogen bonding, less polar. Because if 1 through 4, that's really also ranked in terms of polarity. The greatest polarity is your ion. Hydrogen bonding is a very polar thing. And thus it's not going to like the nonpolar hexane. That should be more soluble in hexane. Which should be more soluble in water? This one. Why? Well, the first thing you say it's more polar because it has more hydrogen bonding. You got to be careful. Can this hydrogen bond to water? It can. It actually can hydrogen bond to water. But if you show all the hydrogen bonding that's possible, you're going to get more hydrogen bonding here with water. Because this has the two H bond donors. They can hydrogen bond with the oxygen of water, where that does not. The one on the left has more hydrogen bonding potential, and you would predict it to be more soluble in water. You got to be careful. Does that mean it is soluble in water? I actually doubt it is, because I know this compound. Maybe it's soluble in hot water. So you got to be careful about making an absolute prediction versus making a comparison. Comparisons are usually easier. I predict it to be more soluble in water, but is it? I don't know. It does have a lot of plain hydrocarbon in there. Okay, solvents. You got to get used to solvents. Here's a list. This is my list. I divide these. You got water versus organic solvents. Organic solvents can be divided in between polar and nonpolar. You got to be careful. I call these nonpolar. Hexane clearly nonpolar. Ether, though, that's actually a polar molecule. Because if you show dipoles in the tetrahedral nature, they don't cancel. So why am I calling it nonpolar? It's because these are not soluble in water. This is a very general statement, nonpolar. That's relative to those. They're less polar than these. Okay. Really, the only one over here that's truly nonpolar is hexane, or maybe toluene. These don't mix with water. All of these mix with water. Acetone, ethanol, DMSO, dimethylformamide, DMF. Okay. Ethyl acetate. Over there. These you do not need to learn. You need to use this as a reference and start learning them as we go along. By the end of Organic 2, you should know most of these. Okay? Reference page. Understand how they're presented. Ask any questions if something looks odd. When we talk about extractions, where you have to have two phases, an aqueous phase and then an organic phase. These are the ones you would use for extraction, because you get two phases with water. You can't extract with these. They mix with water and you only have one phase. Okay? H2O, sometimes called the universal solvent, but that's really no good. Very poor for organics, unless they're highly polar organics. Otherwise, most organics are not going to dissolve in water that well. H2O are no good for salts, ionic compounds, ion pairs. You can read that right there a little bit. There's an extraction. Please look at that. We'll look. That's also in the other handout, I believe. We'll look at that a little bit later. Let's look at a couple of examples of IMFs. This is the drug, what is this, Crestor? You may have seen a commercial or two about that. Are you down with Crestor? This is the drug binding to the enzyme that it inhibits, HMG reductase. How does the drug bind to the enzyme? Different IMFs. You got to be careful what you see out there. For example, I don't know what they're showing right here. Looks like they're showing an oxygen interacting with an oxygen. I don't know. What they should have showed is that H there, the oxygen interacting with the H. Yeah? I'm trying to show how to bond here, but whoever put this together is not too good. Here's an F lone pair interacting with an H's on the end. These are hydrogen bonding. Okay, so it's good. Hydrogen bonding. Yeah. I mean, look, come on.
This is not a good label.
Really, you need to look at this and find the arrows and make it better. Okay. You could call this hydrogen bonding, but you could also call it what? Ionic attraction. Because you got this negative oxygen here and an ammonium ion that you can call it ionic attraction. That's the more major one there. Basically, it's held in there by all these IMFs. What are these hydrophobic bonds? Van der Waals attraction. What does hydrophobic mean to you? Water hating?
Yes.
Water, it's just hydrocarbon. They're called hydrophobic bonds. So you got to be open to other terminology. But look at this. You got this hydrocarbon here. These amino acids have hydrocarbon side chains. You know, maybe like this on a valine or leucine or something. And then you get these hydrocarbons just sort of interacting. That's not hydrogen bonding, that's just trying to illustrate some type of IMF interaction. By what type of interaction? Van der Waals. Now that's going to be pretty weak. Well, maybe it's important enough to help the binding. And maybe that's why they decided to put this little hydrocarbon portion of the molecule so we can interact with those amino acids in the enzyme. You can look at the things below, just other applications. Many of these just come from your textbook. I don't want to take time to explain them here. I'm just sort of pointing them out so you can look at. For example, soap. You look at this molecule, it has this sort of ionic end, and then it has this long sort of fatty side chain, and you can envision sort of polar interactions here, and then this is going to interact with nonpolar stuff. Why does it act as a soap? Well, when you bathe, typically you bathe with water. You're trying to remove oils. Well, this interacts with the water. This portion interacts with the oils, and it sort of brings it all together. And it may interact like this. Other applications, real quick. Here's two different drugs, although they're pretty darn similar. Prilosec and Nexium, used for what? Gastric reflux or heartburn type of stuff. What's the difference in these two? Really nothing, but the difference here is this one is the magnesium salt, where the nitrogen is an anion. But this one, the nitrogen has the proton and it's neutral. Okay. Which drug would be more soluble in water?
Number 2.
The one that's ionic. We said ionic is going to have more water solubility. Okay? Now, big difference in these is I think this one will cost you a lot more money because it's newer on patent. This is no longer on patent, or it used not to be. Maybe that's no longer on patent either. Thus, if it's not on patent, you can get generic of this and be cheaper. But guess what? When this goes into the stomach, what happens to this anion? You treat it with H+, what's going to happen? These electrons will attack the H+, and you'll put the H on. So when this gets into the stomach, it's going to exist like this. Okay? Then you wonder why you spent all your money on that. They probably got a new patent because they argued that this is going to dissolve faster in the stomach. But once it's dissolved, it's got the proton on it. Because starting on Monday, we'll be starting with acid-base chemistry. We'll need to know this chemistry. We'll need to know how to use pKa's to judge if this is going to happen, et cetera, et cetera. Question?
I just wanted to ask if would that be the purpose to take nitrogen and reduce the acidity of the sunlight?
Well, if you just want to reduce the acidity, you can take alpha seltzer, bicarb.
Yeah, well,
That's 50 cents.
what do you think? Like, hybridization?
That's an expensive pH reducer. Okay, guys, please be looking at acid-base chemistry. We'll start that on Monday. See what type of questions there are for the physical properties. See some of you in lab. We'll meet downstairs over here. Have a good day, guys.
Oh shit.
What do you decide what sodium
That shit.
because that would be a hard one to do when you have fire.
Uncomfortable.
So when you pick